DC motor, and it is a application for drone motors, and that's the thing. And you can see the TIVA board will be sending the control signals and PWM signals to the DRV8313 IC, which is nothing, which has 3 half bridges, which then controls the BLDC motor by sending the 3-phase signals. So this is how it works. And if you ask me where is DRV8313, you can see it's here, like in the back side of the PCB. This is an SMD device. And basically what is happening is that TIVA-C generates the PWM and the control logic, and it sends over to DRV83, which then controls the BLDC motor. And for PWM initialization, I'm using the hardware PWM, and the frequency range can be from 4 Hz to 50 Hz or more. And for software PWM, like I'm using for enable pins, like stick timer for this. And I'm also doing the ADC integration and computation logic. And this is how I'm sending signals from TIVA to DRV83. So since there are, it's a 3-phase, there are 6 MOSFETs. One, like upper MOSFETs will be driven by IN1, IN2, IN3 inputs, and lower MOSFETs will be driven by EN1, EN2, EN3 inputs. And for driving the upper MOSFETs, I'm using the hardware PWM itself. And for driving the lower side MOSFETs, which comes for the enable signals, I'll be using the stick timer to generate it. So my idea is to send 3 signals, like 3 PWM signals for the IN1, IN2, IN3, which is 120-degree phase shifted, because that is how the 3-phase motor working principle is. So what I'll be doing is I'll be sending a low frequency PWM, say 10 Hz. And the enable signals will be high frequency PWM, like 2 kilohertz with the variable duty cycle. So I'll be doing amplitude modulation. So this leads to lower overall average voltage, because for the motor working, I'll be giving like 12 volt supply for the DRV8313, which is required. And I will be doing, like as mentioned, low frequency and high frequency modulation, so that average will be less, so it won't heat up, and it's like a good method which I found useful. And you can see the DRV83 is like a gate driver and it's the main power stage, and it's carefully laid out PCB so that to ensure proper thermal management, current flow, and signal integrity. And you can see in the PCB board, I also have a few of the op amps. Like these op amps are nothing but the comparators, which helps in the feedback, like the back EMF, whenever the motor rotates, there will be back EMF generated, and that voltage will be tapped by like compared, and then it can be used as a feedback. That's how it was designed, where I'll be taking the neutral point and all the phases will be going to this, and this one will be going to the TIVA-C as a closed loop feedback. And also to limit the current, I'm using the current chopping method, where I'll be using the current sense resistors and then comparing with the reference voltage. And when this goes high, TIVA will get to know, and then it can change the phase. So you can see this 1 ohm resistor, which has like 1 watt good capability. So this is mainly used for the current sensing part. And all these capacitors, everything are like the compensation required for the proper operation of the DRV8313 IC. So this is how it was implemented. Both the hardware and software was done to implement this low-cost ESC controller. The main motivation was that I could have used like direct 3-phase thing, but I wanted to develop it in a low-cost way and also get to explore in both hardware and software thing. So this is about my project. So yeah, thank you.